Let's talk about that chapter or that part of that chapter. Mathematically equivalent does not need to be numerically equivalent. Let's talk about an example of statistics. Let's talk about a sample and let's keep things as easy as possible. So let's talk about a sample of 3 values. And let's say that this sample consists of the values 2, 3, and 6. In this case, these are integers. Normally, these were some numbers, some crude numbers, but to keep things simple, I will prefer these numbers. So, what are the basic statistic values? These are the mean value and the standard deviation. What is the mean value? Everybody knows it's the sum divided by the number of elements. In this case, we have 3 elements, so we divide by 3, and so we get 11 divided by 3. What is 3.6666 and so on. What is the standard deviation? Maybe you know it. If not, I will tell you now. First, we can calculate the variance, the empirical variance, and the formula is take the first value, subtract the mean value, and square this difference. Do so with every value and divide that by, not by 3, but 1 less than the number of elements. So in this case, divide by 2. And if you do that calculation on your calculator, then the result is 4.33. As we can see here, and what is the standard deviation? This is the square root of this variance, so it's square root of 4.33. And we get the value 2.081. So it's no rounding, but it's cutting the sequence. Okay, this is the variance and this is the standard deviation and this is the formula. But there's a second variant for calculating the variance or the standard deviation, and this is square the elements of the sample and add the squares, then subtract the number of elements, which is 3, times the mean value squared, and divide that by 2. And if we do that, we will get exactly the same result. We performed all the calculations with the exact mean value, not any rounding in the game. And as long as the mean value, if there is no rounding, then this formula and this formula will always produce the same value. This is not obvious. We will see later why these are equivalent. It's absolutely not obvious why this is really true. Okay, so the standard deviation again is the square root, and so it's again 2.0816 and so on. As long as there is no rounding here, as long as this is true, these formulas will always produce exactly the same result. But so let's say we use the rounded version of that number, which is 3.7. Rounded version, 1 digit after the decimal point. So let's check what is the result of this formula. And let's check what is the result of that formula. This time the result here is 4.335. And then the standard deviation is the square root. And we get 2.082 something. Not exactly the same result as above, but close to that value. And what do we get using the second formula here? This time we get 3.96. And the square root this time is 1.99. Okay, so the results are different. Which one is the better one? The better one clearly, obviously, is this. Variant 1 and variant 2 is not completely bad, but away from the correct value. So this is very, very surprising, and in my view, this is completely counterintuitive. You have two formulas producing the same answer as long as the input here, the mean value, is at the non-rounded version. But if you exchange the mean value by a rounded version of the mean value, then the formulas no longer produce the same answer. For me, this is completely counterintuitive. And as long as I did not do these calculations on my own electronic calculator or on my sheet, you can also do these calculations without electronic calculator using fractions, then I say this is impossible. But I see, no, it's not impossible, it's possible. This really happens. And for me, this is completely counterintuitive. Okay, so let's go back to the script. Here are the formulas. And this is variant 1. And here is the formula in variant 2. Being a student of statistics, which formula would you prefer if you have an electronic calculator but only a very simple one? Then most likely this formula is not so kind, because you have to type in the mean value, in this case 3 times. And in this formula version only 1 times. So it's more simple to use this formula. Unfortunately, this formula, at least in this example, produces the worst answer. Then in the script I use an example with 7 values in the sample, and here are the calculations. And now we want to understand, how is that possible? How can that be really true? And this we will do here. And I will also do that calculation on my paper. Let's examine this formula in any case. Okay, so let's do this calculation. What is happening? I take the first value and then I subtract the mean value. But if using a rounded version, then we subtract the mean value, the real mean value, but this mean value is disturbed a little bit. So let's say it's disturbed by an epsilon. Epsilon is some small number. So we use this instead of that. And then we square that and we do this calculation for all the values in the sample. And we divide that by n minus 1, but I don't want to write that n minus 1 because it always stays n minus 1. Okay, what happens here? What is the square of that? It's the square here, minus 2 times the product, plus the square of that. And let's do so for the first summand and for all the others as well. So let's square that. That squared plus 2 times the product plus this one squared. And also do the same for x2. This will stay the same for x2. This will stay the same for x2. This will stay the same for x2. But this will have to be exchanged by x2 and xn. And so there are more terms here. Okay, and if we do that for all the x1, x2, x3, and so on, then we get not only x1 squared plus also x2 squared plus also x all them squared. And now we have all these terms out of these summands. Then we get minus 2 times here x1, next time x2, next time x3, and so on. This is always the same, so we can factor out something. And this is x1 plus x2 and so on times. Okay, so now we have all these terms. Then we get that term in every part here, so we have this one n times. Then also this one we will get n times, and we will get this one n times. Now this one is the sum of all the values in the sample. So this has a lot to do with the mean value. The mean value is the sum divided by n. This is the sum without dividing it by n. So we can also write that by n times the mean value. Why do we do? Because then the formula, there will happen something which is helpful. Okay, so what can we do now? We can write here minus 2 times n times mean of the values squared minus 2 times n times that. Okay? And now what happens? Here nothing. And now we have that plus that minus 2 times this plus 1 times this, so we get minus n times. And what do we have here? Here we have this minus and this plus, so this completely cancels out, plus n times epsilon squared. Okay, so now we are here, and now we can take that fraction and we can use that part here and then that part here. And then we see the following: if epsilon is 0, then this part is 0. So we also see by this calculation that the two variants are equivalent. If epsilon is 0, this formula will produce the same answer as this formula will do. And now we can analyze the second variant, and that's what we do here. Okay. Here in this case, calculation is much simpler because we expand this bracket x mean value squared. We have that here. There's a minus. And then 2 times x squared times epsilon. That's what we have here. And epsilon squared times n here. So this calculation is quite short. And then we can take that fraction, take the first part and get that. And here the second part we have here, and the third part we have here. And now it's clear that if we use the rounded version of the mean value, these two formulas don't produce the same answer. Now we have a clear sight on that. That is what I think is counterintuitive, but here we see this is really true. And now we can analyze what is worse, having this part here or having these parts here. And the answer is quite easy. This part is exactly the same here and here, only there's a plus or a minus, but that means that the error one times we overestimate and the other time we underestimate. But on top of that, we have here a second part. And here, what is happening? It starts with n over n minus 1, the same as here. Then we have an epsilon instead of an epsilon squared, and then we have a mean value. So here an epsilon is exchanged by the mean value. And which is the greater value? Is it epsilon or is it the mean value? Let's see here. If we use the rounded version, what is the epsilon here? the epsilon this time is 0.03. So the epsilon is the rounding taking part using the rounded version of the mean value. So the value here is always less, much less than the mean value. Epsilon is always another magnitude than this value because rounding is done so that the value is changed only a little. So that makes clear that this value is a very big one compared to that value. And this shows that this formula here always produces answers which are more far away from the value here. And so it's clear that this formula is the numerically better one if we use a rounded version of the mean value. And please remember, calculating in numerics is always, there are always rounded versions of numbers. So it's clear that this formula, variant 1, is much better numerically than the other one. Unfortunately, being a student and using a simple electronic calculator, this formula is much easier to use than that formula. But okay, and now, more alarming, we also have problems if we use an electronic calculator which is not a simple one. Example, if we use MATLAB, if we use Octave. So if we produce 1 million numbers which are very close together, what is happening here? We take 2 million plus a number between 0 and 1. So we have either 2 million or 2 million point something. So we have 1 million numbers which are very close together. We have the following situation. Here is the 0. Here is the 2 million, and here is the 2 million plus 1. And all the values are in this interval. And we have 1 million of them. And this is a really bad situation. Having values far away from 0 and then very close together. If we are interested in the standard deviation in this example, then things get really interesting, also if we use MATLAB or Octave. Here we calculate the mean value of these numbers. This is the number more or less 2.5 million, and then we can use variance 1, our first variant, to calculate. We subtract from every entry the mean value, then we square all these, and then we sum these squares and divide by n-1. In this case here, the answer was 0.0834, which is a quite good answer, as we will see later. And using the second variant, let's square every entry, sum this square, and then subtract n times the mean value squared. And using that variant in this example, the answer was 0.1546. These answers are very far away. So it's a really big difference which formula do we use. Okay, if you have a numerical calculation in 2 variants and the 2 variants do not produce the same answer, then either one value is nonsense or both values are nonsense. If we are in the first case, then you can't know which one is the correct one and which one is the bad one. In this example, this is a very good answer and this is a very bad answer. And I want to show you why. I can tell you that if you do some statistical analysis, this here, this is close to a uniformly distributed random variable, and having that you can analyze the variance And in this case, the variance is 0.0834. And this is really clear. This answer must be complete nonsense. If this is not really satisfying, when I wrote that script, I said, okay, you can never know what happens if you use the random variable. Then let's exchange the random command by a linspace, so you know the numbers, and then you can analyze that on a piece of paper. And I did that, and this analysis will take 5 or 10 minutes, and then I will get that answer. Okay, this is the correct answer. In this situation, I know what is the correct answer if there's no rounding. Okay, and if I do so, then I get here from variant 1 this answer, which is completely correct. And as we can see here, comparing these two values, but using the second variant, I will get 0.4280. So this is 5 times this value. We are very, very far away. So variant 2 is really, really bad in this situation, but this has to do with the speciality that we are far away from 0 and then close together in a very narrow band. Okay, what is the conclusion of our example? What did I want to say? This was not an easy analysis, okay? But it has to do with statistics, and it has to do with things you have to calculate doing statistics. And there are 2 variants, and they are mathematically equivalent. And if they're equivalent, normal people say, okay, then you can choose which one do you want to use. Doing numerics, if you're in the situation that there are 2 variants, then it's very interesting which one is the better one. And it's not clear from the beginning which one. You have to analyze these formulas. And in this situation, the analysis of a person who did a lot of numerics so far says, okay, in this situation, you take the difference of 2 values which are very close together, number minus mean value. So in this situation, it's a number between 2 millions and 2 millions plus 1 minus 2 millions and a half. So we have large numbers which are close together. So this is not a good idea, but we have no choice. This is the kind the formula is defined. So we have to do that thing, but we are kind of alarmed. Okay, and so we get this result. Here we subtract also large numbers. This time, this sum is a very large number, much larger. In our situation, 2 million something, you square 2 million something. So you get 2 or 4 millions of millions. And then you sum them, and then you subtract here again a very large number. And this time, this subtraction is of much larger numbers. Much larger numbers. And that means this is even worse. This is bad, and this is worse. You subtract much larger number, and it's not a good idea to blow up numbers and then do subtraction. The better idea is don't blow up the numbers, and so it's more or less clear that this is the worse idea to calculate the variance than that idea being in a numerical situation. Okay? I hope this became clear. I hope this was not too complicated. As an example, I think it's a very, very good example because it comes from the real world and it does not use things like that. This here, it was completely nonsense to blow up the number, and then to subtract. But in our situation, okay, we blew up the number and then we subtract it. And this is a natural idea